Hi everybody. Let's go ahead and take a look at what PoCoE actually means with a couple of examples. So PoCoE is actually an acronym. It stands for the Principle of Conservation of Energy, which means energy is being conserved. Typically we would say that energy can't be, and say it with me if you know it, created or destroyed. Okay, it's typically where they leave it. But we know that energy is changing all the time. That explains a lot of phenomena we see. So we know that it can be changed. So let's go ahead and take a look at what that looks like for our situation here. So I got a couple examples here. Our first one we're going to do is a roller coaster. So let's imagine we have this roller coaster here. It's got a hill in the middle, a hill at the end, something like that. Just add some details. So there's our typical, very thrilling roller coaster. And let's say our little car for the roller coaster is way over here. Okay, let's think about what the energy for that car might look like. So I actually do want to do a sort of pie chart thing right now. So let's go ahead for this roller coaster right here. That's an awful circle. Okay, what might our energy for this look like? So if we imagine this car needs some speed to be able to go up this hill, correct? So it's going to have some kinetic energy, energy of motion, right? And if you notice, the car is a little bit above the ground, so it's also going to have some gravitational potential energy as well, energy due to the object's height. So let's go ahead, and I'm actually going to represent this too. Again, I have this little pie chart thing, and you guys can make this at home too. It's just two circles with a slit down them. So remember, we said energy can't be created or destroyed, but it can be changed. So again, when I rotate this, I see that the total energy for this car is not changing at all. It always has 100% of its energy that it had. All right, but it can be changed. So if we have a little bit of kinetic, actually we're probably gonna have a lot of kinetic, right? Because usually you need to get a little speed boost on the roller coaster to be able to go up as high as possible. So let's say maybe it came from a higher drop over here. I don't know. Okay, so let's say maybe it has, I don't know, something like that. So let's draw our pie chart something like that. Say mostly kinetic with a little bit of potential. This is potential. And this one is kinetic. So it has a lot of speed going up there. What is that energy going to look like at the top? So you can pause and think for a second if you would like. Remember what we said over here, potential energy has to do with how high the object is in this case. That's gravitational potential energy. So as this object is getting higher, it's going to be getting more potential energy. And isn't it true that if you like throw something up in the air, it like slows down until it stops and then it comes back down, right? So it's going to be also losing kinetic. So if we show that with our pie chart, gaining potential also means we're losing kinetic. That's why it's slowing down, right? So let's say this is the very top that it's ever going to go. So usually they design the roller coasters so it has absolute maximum potential energy. All right, so let's say it's right here, right before it goes over, it has 100% potential energy. Right, it got the most out of it that it could. Right. Right now when it's going down, it's going to look like right at the bottom here, if we imagine that. So again, now let's reverse it. Potential energy has to do with height. So if we're losing height, we're going to be losing potential energy, meaning we're gaining kinetic energy. Okay? All right, so we're gaining kinetic energy, and if they designed it right, we should have a lot of speed down here. We should have the max speed that is going at the very bottom of the hill, because it should use all its energy up and convert all that potential into kinetic. All right, and we got a couple more scenarios. All right, this little hill right here. Let's go ahead and say we got a car here on this hill. Now, It came from right out of this bottom of this like bottom of the hill, coming back upwards. It's going to turn some of that kinetic energy back into potential because it went up. But is it going to be all the way over here? No, it's not. It's not, because like that total, this car did not travel as high, so it couldn't have gotten that much more potential out of it. So let's say most of the energy is still in kinetic energy, because you probably want this roller coaster going pretty fast as it comes down this hill, right? So let's go ahead and draw it something like this, where we have our majority kinetic again. And then just this little sliver is going to be our potential. All right, one more scenario is over here. I didn't draw it very well. Let's imagine the car over here came to a stop. I draw a stop sign very well. Okay, stop sign, it has to stop there. Well, now all of that kinetic energy has to be going somewhere, right? Because if it needs to stop, it can't have any kinetic energy, because that's energy of motion. If it's moving, it's going to have some kinetic energy. So what do we do with this kinetic energy? Well, they could. I mean, you could imagine they put like a big ramp on the side, and then it converts it all into potential energy and just be done with it. But then it's going to go backwards. It's going to come back down, okay? So they need to do something else to this energy. And what's important to realize is that energy is not just potential energy and kinetic energy. There's other forms of this energy. So let's go ahead and add a piece of energy. I have another little pie chart here, and let's say there is this other form in here. So if we had a lot of kinetic and some potential, again, if we have a lot of kinetic, we still have some potential. Let's say this kinetic goes away. This is kind of hard to do. Say this kinetic energy goes away, and let's spiral this all out. All right, well, we don't have much potential right now, but what we do have is some, there we go. All right, so that other form can change into other forms, right? That kinetic energy can take other forms. And then so there was this hidden piece of this pie chart that was behind everything. It wasn't being used at the time, but when it's needed, I mean, we have this other energy to look at too. So what might this look like? Well, at the very end, let's say we got a pie chart here. If it's totally stopped, let's just say it's all this other energy. And what is this other energy? Well, if you know anything about like things with brakes, like a car or like a roller coaster like this, when the brakes are applied, the brakes are going to get hot. So one thing might be like thermal energy, the brakes heating up. Or you could say sound energy, because you might hear the squealing of the brakes. Now, I want to go ahead and show this to you right now with this online program. So let's go ahead and flip over to this. This is called Energy Skate Park. So starting off here, let's go on friction one. So what this is, I want to show you guys some proofs of the stuff we just talked about. So I got the skater over here, and if I go ahead and pick her up and drag her to the top of the hill, notice on the left side in the bar graph over here, we have our energies. All right, so as I'm lifting her up, she's getting potential energy because it depends on her height. Notice she doesn't have any kinetic energy right now because she's not moving. And you notice this, there's a little speedometer in the middle too. That tells you your speed. So when I let go, she just starts going. You can watch at the very top of each side. Notice she'll go to the same exact spot. So I'm going to actually start her over again. Start her right at 6. And you'll notice that she will go up to 6 on this side. All right, so that's showing us that, because remember, energy cannot be created or destroyed. Our total energy is staying the same. Notice that bar is not moving. if energy could be created, well then what would happen is she would go flying off of this thing because she's getting more energy than she had in the beginning, so she goes flying off. If it could be destroyed, then somehow one of these bars would be shrinking, but this total would be kind of total would be shrinking as well, right? And that we don't see that happening, right? So one other thing too is, if you didn't believe me, let me switch back to this real quick. If you didn't believe me about these things happening, potential being the highest in the top of the hill, kinetic being the highest at the bottom of the hill, take a look at this. So notice, I'll even pause it right at the right at the bottom. If I move, I don't think I can move her. Nope. All right, right at the top, potential is the highest. Let's go in slow-mo actually. Pretty close, yeah. So look at that, right at the bottom, kinetic energy is 100%. Because all her potential, she's like on the ground, all her potential energy is now gone. Okay, let's keep her going. All right, now I want to go ahead and introduce something called friction. Well, in the real world, in our world, we have friction. So friction is what caused the roller coaster to break. So if I turn on some friction, we'll notice, I'll just put it on like medium. We'll notice now, every time she goes down up and down this ramp, she's gaining some thermal energy. And then that's just exactly what, I tried to show that in that pie chart. Right now we got this other energy that kind of came out of nowhere, and it's slowly going all to friction. Right? And then eventually she'll be stopped. Because the friction kind of stole the energy from kinetic and potential. So she doesn't have enough energy to keep moving and get high enough. All right, let's see, I hope that helped. Let's go to another example. Take a look at this next example, burning some wood, like in a fire. Okay, so let's say we have some logs. Throw some logs here. And we got a fire. All right, there's our fire. Okay, so what energy is this starting with? We're using some energy in these logs, right? The energy from a fire is coming from the thing you're burning, right? So these have some form of energy, and it's kind of stored up in those logs. So it's going to be a potential energy. And you might have remembered that we've talked about chemical potential energy. Chemical meaning the energy is coming from what the object is made of. So it has energy just because of what it's made of. Typically, we have to get a fire started with something. So that might have gotten some energy from another place. Let's say, usually you got to light it. So let's draw like a lighter over here. I'm not good at drawing a lighter. All right, there's our lighter. And what our lighter did is it used its chemical potential energy from here, and it made some thermal energy, right? Because it's using this little fire to heat up this log and get this burning. So we use a little bit of energy in this lighter, that I guess butane in the lighter, to go ahead and generate some heat that heats up the logs enough so they can start burning, and then we're able to use this chemical potential energy to have the full fire. And then, so what are some energies that fire then can produce? So we have things like, the obvious one would be like thermal energy again, because we can feel the heat of the fire. We have some, if you've been to like a campfire, you might know that that crackling sound of the logs is like kind of bursting. So we get this sound energy coming from them, like the cracking of the logs. And one more, also obvious, some point of the fire is to generate some light. So that is radiant energy. And it also happens in two ways. So we can see can see the light. It lights up people sitting around the campfire. But also, if you go ahead and put your hand in front of your face when you're sitting in front of a fire, it blocks that heat from hitting your face. And I'm sure some of you have experienced that. So we also have a way of blocking other types of heat, and we'll talk about that towards the end of this unit. But there's also a thermal component to that radiant heat as well. We can feel that heat far away. We don't have to be in the fire to feel it. So there's also another component there. All right, one more example. This one is kind of different. Electrical power plants. I want you guys to be able to see what this kind of looks like, so I go ahead and show you this right now. When you just Google electric power plant, if you've never seen one, or just so you can get an image of what it might look like, you'll see, I see a lot of things with these big tall like smokestacks. Oftentimes you'll see these cool, I think they're nuclear reactor sites. But just to get a general overview, there are some like diagrams too here that we're gonna just kind of look at right now. But the point of that is there's a lot going on in generating electricity. So let's take a look how that starts. Usually, to start off with, the point of all those big like smokestacks and tower things are to burn some sort of fuel in the beginning. So you may have heard of a coal power plant. So let's say we got some coal down here. Looks like this. So we got some coal in there, and we're going to burn that coal. Okay, so that coal's on fire. What type of energy are we using down here in this coal? We're releasing some type of energy that's stored there. It's stored as chemical potential energy. So it's stored down here. We're releasing it. We're burning it, so we're using thermal energy. And the point of using this fuel down here is so we can heat up water, which sounds kind of weird. But if you look at, let me just go ahead and transition back to this. All of these images, let me go ahead and blow that one up a little bit. You can see all of that is actually just like steam. It's water vapor. It's essentially a cloud coming out of the towers. All right? It's not pollution like some people think. It's just water. So what they're doing here is they're heating up water. So let's draw a tank of water, let's say, or a pipe of water. What that's going to do is it's going to make steam, like we just saw. So we got steam coming out. So going to the beginning, chemical potential energy in the coal is heated up, burned. We're using that energy, releasing it as heat. That heat's going to the water, and it's turning it into steam. Okay, and what we're doing with that steam is we're going to make something move. So let's draw. This is what's called a turbine. Essentially, if you've ever seen like a water wheel, like on a old sawmill or like the apple orchard, something like that. It's essentially kind of like that. Basically, the steam gets kind of trapped in these things, and it's going to push it around and cause it to turn. Okay, so we got this turbine here, and this thing turning is like a key part. This thing turning, if we're turning something into motion, we're giving it some kinetic energy. So we're giving that kinetic energy. That kinetic energy is going to be transferred. And I know this one is complicated, but bear with me. Transferred to a generator, which essentially is basically a motor. And then so when this thing spins, it's actually going to produce electricity. So that's what we get down here. Basically, they use this giant generator. We've got some wires coming out of it, essentially, and then wires going out to the telephone poles that you can use for your house. So, again, going over this whole process, they use the chemical potential energy in the coal, heat it up, heat up the water, and then the water turns steam, which turns a turbine, which spins a generator, which then generates electricity. All right, I hope these examples helped.